Early 1944, Wright Field, Dayton, Ohio. A test pilot rested his palm on the throttle of a P-51 Mustang and pushed it beyond its normal war emergency limits. The engine thundered as manifold pressure surged to 75 inches of mercury, powered by a new experimental fuel known simply as Grade 150. The airspeed indicator swept upward into ranges Allied fighters had never reached before. At 25,000 feet, the Mustang was slicing through the air at 448 miles per hour. The engineers monitoring from the ground exchanged looks as the radio carried the pilot's astonished report. This wasn't a minor improvement, this was a transformation contained inside purple-tinted high-performance gasoline, a chemical leap so significant it rendered outdated every Luftwaffe assumption about American fighter capability. The war in Europe was about to pivot, and the trigger wasn't a new aircraft design or tactical brilliance, it was fuel that enabled existing aircraft to perform far beyond German predictions. What the Luftwaffe had yet to realize was that American and British fuel scientists had achieved something the Third Reich's synthetic fuel industry could never match. While German fighters struggled on before fuel rated around 91 octane and their top C3 blends barely reached the level of Allied 130 grade gasoline, Allied refineries were producing aviation fuel with a performance number of 150. The consequences were enormous. A P-51 Mustang burning standard 130 grade fuel could achieve 437 miles per hour at 25,000 feet. The same Mustang, at the same altitude, flown by the same pilot, could exceed 448 miles per hour on 150 grade fuel. German pilots who had already learned to fear the Mustang's high altitude range and speed were about to face the reality that the Americans had fundamentally shifted the air combat balance. The Messerschmitt Bf 109G, the Luftwaffe's mainstay fighter in early 1944, topped out near 400 miles per hour at altitude. The Focke-Wulf 198 could barely reach 408 miles per hour under the best circumstances. Against Mustangs on 130 grade fuel, German pilots could still try to pick favorable engagements. Against Mustangs running on 150 grade fuel, they were locked into a losing contest, one that no amount of skill or tactical finesse could undo. This advantage did not begin with the war, but with the quiet pre-war work of petroleum chemists who understood that octane ratings measured how much an air-fuel mixture could be compressed before detonating prematurely. Higher octane allowed higher compression ratios, which meant more power per combustion cycle. More power meant faster aircraft with greater altitude capability. The science was simple, producing that fuel in quantity was not. In 1940, when Europe was already engulfed in conflict, American aviation gasoline was still centered around 87 octane, a level fine for civilian aircraft but hopelessly insufficient for frontline fighters. The British, desperate for every possible edge against the numerically dominant Luftwaffe, collaborated with American oil companies to develop 100-octane aviation fuel, which arrived just in time for the Battle of Britain. Its impact was immediate. Spitfires and Hurricanes gained 30 to 40 miles per hour at altitude, and their climb rates jumped by 500 to 1,000 feet per minute. German pilots who had once enjoyed technical superiority suddenly found themselves matched. The later development of 130 grade fuel pushed Allied performance even further. This rich mixture 130 performance fuel became the foundation of Allied air power throughout 1943. It powered Rolls-Royce Merlins and Spitfires and Mustangs, Allison engines and P-38 Lightnings, and the huge Pratt & Whitney R2800 radials and P-47 Thunderbolts. Production expanded rapidly, driven by General James Doolittle, an early champion of high-octane aviation fuel who had spent the 1930s pushing both industry and military leaders to prioritize advanced gasoline development. By 1943, 17 Allied refineries were producing high-octane fuel using the catalytic cracking method perfected by French-born engineer Eugene Houdry. American plants alone were manufacturing millions of gallons per month, more than enough to power the strategic bombing offensive and the growing fighter forces that shielded the bombers. Germany, by comparison, remained trapped by its dependence on synthetic fuel derived from coal. The Bergius hydrogenation process that converted coal into aviation gasoline was technologically sound but painfully slow and resource-heavy. Even at peak capacity, Germany could only produce a fraction of the high-octane output pouring from Allied refineries. Most German fighters were forced to rely on before fuel rated at roughly 91 octane, nowhere near the level needed to match the performance Allied fighters were reaching in 1944. Their premium C3 fuel used primarily in BMW 801 powered Focke-Wulf 190s and select Messerschmitt variants was roughly equivalent to Allied 1130 grade fuel but available in far more limited quantities, By 1944, perhaps two-thirds of German aviation fuel production was C3 grade, but this still represented only a small fraction of what the Allies were producing. Understanding fuel performance requires grasping a fundamental principle of internal combustion engines. Octane ratings measure detonation resistance. When a piston compresses the air-fuel mixture during the compression stroke, temperature and pressure increase dramatically. If the fuel spontaneously ignites before the spark plug fires, the result is detonation, an uncontrolled explosion rather than a controlled burn. Detonation creates shock waves that damage or destroy engine components. Higher octane ratings mean the fuel can withstand higher compression without detonating. Octane ratings by definition cannot exceed 100 because 100 octane means detonation resistance equivalent to pure isooctane, the reference standard. Performance numbers measure how much better than pure isooctane a fuel can perform. A fuel with a performance number of 150 means it can withstand 50% more compression than pure isooctane before detonating. Creating such a fuel required adding anti-in compounds, primarily tetraethyl, and careful blending of aromatic hydrocarbons like toluene and xylene with the base gasoline. British fuel chemists at the Royal Aircraft Establishment tested numerous blends through 1942 and 1943, seeking the optimal combination of anti-NO performance, energy content, and manufacturing practicality. American researchers at Wright Field conducted parallel investigations, sharing data with their British counterparts. By early 1943, both nations had produced experimental batches of what they designated as 150 grade fuel. The designation was somewhat misleading because it implied an octane rating of 150, which was chemically impossible. What it actually meant was a fuel with a performance number of 150 on the rich mixture scale combined with 100 octane performance on the lean mixture scale. This fuel, dyed purple for easy identification, underwent extensive testing through 1943. The results exceeded expectations. Merlin engines running on 150 grade fuel could sustain manifold pressure readings of 75 in of mercury compared to 67 in on 130 grade fuel. This translated directly into increased horsepower. A Packard Merlin Fay 1650-7, the engine that powered the P-51 Mustang, generated 1490 horsepower at standard military power on 130 grade fuel. The same engine running on 150 grade fuel at war emergency power settings generated 1720 horsepower in the P-51B with its V1650-3 Merlin variant. The power increase pushed output to approximately 1,600 horsepower. Flight testing at Wright Field confirmed that the performance gains were substantial across all flight regimes. Maximum speed increased by approximately 25 to 30 miles per hour at altitude. Climb rate improved by several hundred feet per minute. Most importantly, these improvements came with no modifications to the aircraft itself. The same Mustang flown one day on 130 grade fuel and the next day on 150 grade fuel became measurably faster and more capable simply because of what flowed through its fuel lines. The decision to introduce 150 grade fuel to operational fighter squadrons was made in early 1944. The timing was carefully considered. The 8th Air Force, based in England and conducting daylight strategic bombing raids deep into Germany, was suffering unsustainable losses. Despite the arrival of the first P-51 Mustangs in December 1943, German fighter forces were still inflicting heavy casualties on American bomber formations. What American planners needed was not just an escort fighter with long range, but an escort fighter so fast that German interceptors could not easily escape or refuse combat on unfavorable terms. In May 1944, the first operational deliveries of 150 grade fuel arrived in England. Distribution was carefully controlled. Not every fighter group received the new fuel immediately. The 8th Air Force began with select squadrons both to manage supply logistics and to evaluate combat performance. The British Royal Air Force, which had pioneered much of the early testing, also began equipping fighter squadrons with the new fuel. Priority went to units tasked with high-speed interception missions, particularly those hunting German V-1 flying bombs that were beginning to terrorize London in June 1944. The V-1 flew at approximately 400 miles per hour at low altitude. Intercepting these weapons required fighter aircraft capable of matching or exceeding that speed at sea level or low altitude where air density reduced the performance of all aircraft. Hawker Tempests and Spitfire 14s could barely catch the V-1s, Mustangs running standard fuel were marginal. Mustangs running 150 grade fuel had sufficient speed margin to intercept reliably. On June 18, 1944, Major R. E. Turner of the 356th Fighter Squadron destroyed a V-1 flying bomb by tipping its wing using his P-51's wingtip, demonstrating a technique that would be used at least 16 times during the campaign. This maneuver required exceptional speed and precision to position the fighter's wingtip within 6 in of the V-1's wing surface, then use the airflow to roll the flying bomb off course and send it crashing. The first widespread combat use of 150 grade fuel by American P-51 pilots occurred in June 1944, coinciding with the Normandy invasion. Fighter groups of the 8th Air Force, tasked with achieving air superiority over the invasion beaches, flew combat air patrols and bomber escorts using the new fuel. German fighter pilots began reporting encounters with Mustangs that performed beyond what they had previously experienced. Luftwaffe intelligence officers collected pilot reports describing American fighters that could not be caught in any flight regime, that could accelerate away from German interceptors with ease, and that seemed to have power reserves that defied explanation. These reports were initially dismissed as pilot error or exaggeration. German fighter pilots, the intelligence officers reasoned, were tired, outnumbered, and facing mounting losses. Their reports of superior American fighter performance were surely the result of stress and fatigue rather than actual performance increases. This assessment was fundamentally wrong. But the truth would not become clear until after the war. Gerl, a Luftwaffe ace with 275 victories, mostly achieved on the Eastern Front, flew combat missions against American fighters over Germany in 1944. After the war, in interviews conducted during the 1970s and 1980s, R spoke about his encounters with late-war Mustangs. He recalled being shocked at the performance of American fighters during the final year of the war. R, who would later test fly captured American fighters, including the P-51, P-47, and P-38, noted that the Mustang, in particular, impressed him with its speed, climb capability, and high-altitude performance. What R and other German pilots did not realize during combat was that they were facing an aircraft whose performance had been chemically enhanced beyond its design specifications, operating at power settings that the original Mustang engineers had never envisioned. The Merlin engine, designed by Rolls-Royce and produced under license by Packard, had been engineered with careful attention to thermal limits, bearing loads, and detonation margins. Running an engine at higher boost pressures pushed all of these parameters closer to their limits. What made 150 grade fuel revolutionary was that it allowed engines to operate at these extreme settings without the catastrophic detonation that would have destroyed engines running lower grade fuels at the same boost pressures. The chemistry behind this capability involved the complex interaction of fuel molecules, air molecules, heat, and pressure inside the engine's combustion chamber. Tetraethyl lead, the primary antiox additive, worked by interfering with the chemical chain reactions that led to spontaneous ignition. But there were trade-offs. Tetraethyl lead was toxic, requiring careful handling by ground crews. It left deposits on spark plugs, valves, and cylinder walls, increasing maintenance requirements. 150 grade fuel with its very high lead content accelerated these maintenance issues. Fighter groups using the new fuel experienced more frequent spark plug fouling and increased cylinder wear. American maintenance procedures adapted quickly. Spark plug replacement intervals were shortened. Cylinder inspections became more frequent. Engine overhaul schedules were adjusted. The performance gains were judged worth the increased maintenance burden. For pilots, the transition to 150 grade fuel required new operating procedures. Manifold pressure limits were raised. Pilots had to be careful not to overboost engines, particularly at low altitudes where air density was highest. Most significantly, pilots had to learn to manage fuel consumption. 150 grade fuel provided more power, but running at maximum boost consumed fuel rapidly. Escort missions to Berlin and back already pushed the Mustang's range to its limits. Using the new fuel's full capability meant careful fuel management, knowing when to use maximum power and when to throttle back for cruise efficiency. Combat reports from summer and fall 1944 document the transformation. 8th Air Force fighter groups equipped with the new fuel reported higher victory-to-loss ratios and increased ability to intercept German fighters attempting to attack bomber formations. German fighters that had previously been able to make fast slashing attacks and then escape now found themselves unable to outrun pursuing Mustangs. On August 6, 1944, Lieutenant Hollis Bud Nullin of the 357th Fighter Group, flying as part of Operation Frantic missions to Soviet air bases, encountered German fighters over Eastern Europe. Flying his P-51D Hellsbells and powered by 150 grade fuel, Nullin engaged a Messerschmitt Bf 109 flown by G.A. Schack. During the dogfight, the Mustang's superior speed proved critical. Nullin closed the distance quickly and fired a burst that damaged the German fighter's cooling system. With his own fuel and ammunition running low, Nullin ended the chase and gave a parting wave to the German pilot before returning to escort duty. Schack managed to crash-land his disabled aircraft within German-held territory. For the next 40 years, Schack wondered why the American pilot had shown mercy, never realizing that Nullin believed he had only inflicted minor damage rather than delivering a crippling blow. When historians eventually brought the two men together in Germany, Schack admitted that the Mustang's performance far surpassed anything he had encountered before. The speed at which Nullin closed and the surplus power visible during the fight were unlike previous clashes with American fighters. This had a strong psychological impact on Luftwaffe pilots. Already outnumbered and facing overwhelming Allied strength, they now confronted American fighters that seemed to have limitless performance. Their tactical choices shrank. They could attempt large group attacks, refuse combat to save aircraft, or engage in risk being shot down by Mustangs that were faster, more agile, and flown by increasingly confident American pilots. Reichsmarschall Hermann Göring famously declared, after seeing P-51s over Berlin, that he knew the war was lost. His remark captured the Luftwaffe's strategic crisis. The Mustang's long range meant no part of Germany was beyond reach of Allied bombers. The arrival of even more potent fuel in mid-1944 deepened this disaster. Luftwaffe technical teams eventually obtained samples of Allied 150 grade fuel from captured drop tanks or crashed planes. German chemists confirmed what their pilots were reporting: the Americans had created fuel with performance far beyond anything Germany's synthetic program could deliver. Although some late-war batches of C3 fuel approached the 150 grade level, supply was small and quality varied widely. Allied attacks on German fuel facilities, especially the strikes on Luna and other major plants in May and June 1944, tightened the bottleneck further. By late 1944, the Luftwaffe was forced to ration fuel heavily. Fighter units were prioritized, yet still received limited amounts. Training suffered drastically. New pilots arrived at the front with minimal hours, a stark contrast to American pilots who typically logged several hundred hours before combat. Between January and May 1944, before widespread use of 150 grade fuel, American bombers lost about 3 to 6% per mission, high but manageable. From June to December 1944, after the introduction of the new fuel and the achievement of air superiority, losses dropped below 2%. Fighter victories soared. P-51 groups of the 8th, 9th, and 15th Air Forces destroyed roughly 4,950 German aircraft between late 1943 and May 1945, with many of these victories occurring after mid-1944. Germany's pilot corps, experienced but shrinking, was steadily eliminated. By D-Day, June 6, 1944, only 2 Luftwaffe aircraft appeared over the invasion beaches. Though Germany still had thousands of fighters on paper, they lacked fuel, trained pilots, and tactical freedom to use them effectively. Technically, 150 grade fuel deserves special note. Its lean mixture octane rating of 100 meant it resisted engine knock as well as pure iso-octane during cruising. Its rich mixture performance number of 150 meant it could tolerate 50% more compression under full power, allowing engines to generate exceptional output. This combination allowed pilots to cruise efficiently for maximum range, then switch to rich mixtures at high power for combat. Confident that the engine would not detonate even at extreme boost pressures, the handling procedures for 150 grade fuel required special precautions due to the high tetraethyl content. Ground crews wore protective equipment when fueling aircraft. Spills were cleaned up immediately to prevent lead poisoning. Fuel trucks and storage tanks were clearly marked to prevent accidental mixing of fuel grades. Despite these precautions, the safety record was good. Industrial accidents were rare. The transition in operational squadrons required pilot training. Pilots received briefings on the new fuel's properties and updated engine operating procedures. Manifold pressure limits were raised. Operational guidelines specified when and how to use maximum power settings. Aircraft required no modifications. The engines, fuel systems, and all components were compatible with both grades. This compatibility simplified logistics and operations. The production statistics tell a story of industrial mobilization on a scale that Germany could not match. Between May 1944 and April 1945, the 8th Air Force consumed over 53 million gallons of 150-grade fuel. Allied production across all refineries likely exceeded 200 million gallons during operational use. Each gallon required refining infrastructure, chemical additives, including toxic tetraethyl lead, quality control testing, transportation to Europe, storage and secure facilities, and distribution to dozens of airfields. American industrial capacity in 1944 operated at levels that seemed almost miraculous. Factories produced bombers by the thousands, fighters by the tens of thousands. Shipyards launched Liberty ships faster than Germany could sink them. Oil refineries produced aviation gasoline in quantities that exceeded Germany's total fuel production across all grades. This resulted from decades of industrial development, vast natural resources, a protected homeland safe from enemy bombers, and a workforce that included millions of women who took factory jobs to support the war effort. The Royal Air Force used 150-grade fuel extensively in fighter operations over Europe. British squadrons flying Spitfire 14s, Tempest Vs and Mustang 3 ES and 4 received priority allocation of the new fuel. RAF pilots reported similar performance improvements to those experienced by American pilots. The Tempest, already one of the fastest piston engine fighters in service, became even more formidable. Tempest squadrons achieved remarkable success against V-1 flying bombs. Between June and September 1944, RAF 150 Wing Tempest shot down 638 flying bombs, with No. 3 Squadron alone claiming 305. Squadron leader Joseph Bry shot down 59 V-1s, Belgian Ace Squadron leader Remy van Liarde destroyed 44 and Wing Commander Roland Beaumont destroyed 31. The next most successful interceptors were the Mosquito with 623 victories, Spitfire 14 with 303 and Mustang with 232. The performance margin proved valuable in every role. The combat effectiveness of 150-grade fuel was proven repeatedly through late 1944 and early 1945. Fighter groups that received the new fuel reported increased victory claims and reduced losses. By March 1945, virtually every P-51 unit was running the fuel. Combat reports from this period show overwhelmingly one-sided results. German fighters rarely challenged Allied formations effectively. When they did fight, they usually suffered heavy losses. April 1945, missions over Germany often encountered no aerial opposition. The Luftwaffe was finished, destroyed by attrition, fuel shortages, and the systematic elimination of experienced pilots who could not be replaced. On May 8, 1945, Germany surrendered. The air war over Europe ended with absolute Allied air supremacy. This supremacy had many causes. The P-51 Mustang's long range was crucial. American pilot training was excellent. Allied numerical superiority was overwhelming. But the petroleum engineering advantage that 150-grade fuel provided was significant. The purple-dyed gasoline turned good fighters into exceptional fighters, gave Allied pilots confidence, and represented the accumulated technological and industrial might of nations that could outproduce, out-innovate, and ultimately outlast their opponents. Speed matters in aerial combat. A faster fighter can choose when to engage and when to escape. A faster fighter has tactical flexibility that slower opponents lack. When American fighters became demonstrably faster through the combination of excellent airframe design and superior fuel, the Luftwaffe's tactical options narrowed dramatically. The contrast between German and Allied situations in late 1944 and early 1945 was stark. Allied fighters could fly multiple combat missions daily, limited only by pilot fatigue and aircraft maintenance. German fighters often sat grounded for lack of fuel. When they did fly, they operated under strict fuel conservation measures that limited combat capability. A German pilot who burned too much fuel in combat might not have enough to return to base. An Allied pilot could use full power when needed, confident that adequate fuel reserves existed for the return flight. This operational flexibility had strategic implications. Allied fighters could maintain standing patrols, react to threats aggressively, and sustain operations continuously. German fighters had to pick their moments carefully, conserve fuel rigidly, and often break off combat not because they were losing, but because they were running low on fuel. Luftwaffe pilots flew knowing that every sortie might be their last. Not because they might be shot down, but because there might not be fuel for another mission. Allied pilots, by contrast, flew with confidence born from material superiority. They knew their aircraft were fast, their fuel was plentiful, their support system was robust. This confidence translated into more aggressive tactics, better combat results, and higher survival rates. The story of 150 grade fuel is a story about industrial warfare. Victory belonged to the side that could produce not just more aircraft, but better performing aircraft. Not just adequate fuel, but superior fuel. Not just sufficient trained pilots, but an overwhelming surplus of well-trained pilots backed by an industrial base that could replace losses faster than the enemy could inflict them. American and British fuel chemists working in laboratories and refineries never flew combat missions over Germany. They never faced flak or enemy fighters, but their work measured in performance numbers and manifold pressure readings helped decide who controlled the skies over Europe in 1944 and 1945. Every time a P-51 pilot pushed his throttle forward and felt his Mustang surge ahead with power that German fighters could not match, he was benefiting from chemical engineering that transformed crude oil into a fuel that made the exceptional routine. German planners had assumed American fighters would perform within predictable parameters based on aircraft design and standard fuel capabilities. What they encountered instead were fighters whose performance exceeded their calculations, sustained by a fuel production infrastructure so vast and sophisticated that it represented industrial capacity Germany could not counter. By the spring of 1945, as Allied armies overran Germany from east and west, the Luftwaffe had effectively ceased to exist as a coherent fighting force. A few units still flew, often with barely enough fuel for a single sortie. Jet fighters like the Mi-262 represented a technological leap forward, but they came too late and in too few numbers, handicapped by fuel shortages and the absence of experienced pilots who had been systematically destroyed in combat. The final accounting shows the cumulative effect of Allied advantages. American P-51 units across every combat theater carried out hundreds of thousands of sorties. They reported destroying around 4,950 enemy aircraft in aerial combat and an additional 4,131 on the ground. These figures represented far more than just wrecked machines. They reflected the loss of trained pilots, the erosion of German combat experience, and the waste of German industrial effort spent producing replacements that were often eliminated before they could influence the war. Although 150 grade fuel was not the sole reason for this outcome, it played a major supporting role. It provided the critical edge that shifted the air war from a hard-fought contest to a clear Allied advantage. The 448 miles per hour a properly boosted P-51 could reach symbolized not only speed, but also technological progress and industrial strength. This was the factor German strategists failed to foresee, that American fuel chemists and petroleum engineers, working thousands of miles from any front line, could create a resource as decisive as any weapon. That a purple-tinted gasoline could shape air combat as effectively as superior leadership or improved pilot training. That the foundation of air dominance over Europe in 1945 would rest on piston engine compression limits, the anti-knock qualities of aromatic compounds, and aviation fuel performance levels far beyond anything Germany could manufacture. The P-51 Mustangs flying over Berlin in early 1944 were formidable machines. The Mustangs over Berlin in early 1945 were the same aircraft, but fueled with gasoline that made them quicker, stronger, and more formidable. That difference, reflected in octane ratings, power settings, manifold pressure, and airspeed, was one of the many factors that determined control of Europe's skies. Within that outcome lay the destiny of Nazi Germany and a testament to Allied industrial power, expressed through a purple liquid poured into fuel tanks, ignited in high-performance engines, and converted into victory one mission after another.